All right, hello everyone. Let's begin. Welcome to the third seminar of the year. Some logistics first. There is a sign-up sheet. Who has the sign-up sheet? It must be going around. Yeah. Please pass it around. Don't let it get stuck with you because we try to minimize the number of people who need to sign at the end because we have to leave right after the seminar. And only sign if you're in the class. You're taking the class. You don't need to sign if you're not taking the class. Okay, so logistics out of the way. Happy to have our newest faculty member, Xinwei Shen, who joined us just a couple of weeks ago. She did her PhD in Hong Kong University of Science and Technology with Feng Zhang. Then she spent a couple of years at ETH Zurich working with Nikolai Meishausen and Peter Buhlmann. And she will talk to us about distributional causal inference from estimation to simulation.
Thank you, Armin. And I'm glad to see everyone here. So I'll be talking about distributional causal inference from estimation to simulation. So if we talk about causal inference, the first thing we talk about is the estimate of what we are trying to estimate. So conventionally, if we have treatment X, outcome Y, the most common estimate is the average treatment effect. So for example, if we have a binary treatment that takes value 1 or 0, we have then two potential outcomes, Y of 1 and Y of 0. And then we define the difference of their means as the average treatment effect. And some people also move beyond the mean and they look at the quantiles instead. So they take the difference between two quantiles and define that between two quantiles of two potential outcomes and define that as a quantile treatment effect. And by looking at this, we may be wondering if we can move one step further to look at a few quantiles simultaneously, or even ultimately, if we can look at all the quantiles simultaneously, then that gives us the full distribution of the potential outcome. And this is kind of the most comprehensive or most informative estimate we could be looking at, because from there, all the conventional estimates, either ATE or QTE, you can compute them from the full distribution because they are functionals of the full distribution. Okay, so yeah, this is about the estimate. And once we have decided on the estimates, we usually try to develop procedures to estimate or to infer about the estimate, right? That's how we do causal inference. And people have been proposing many excellent causal inference methods. And then the question is how to evaluate them. And it turns out it's a big problem to evaluate causal inference methods or do model selection in causal inference. This is because in many real-world data sets, we don't have access to ground truth counterfactuals. So without ground truth, we can't simply do the standard cross-validation to select models. So that's why being able to simulate data from causal models where you know the ground truth is very important to do model selection and validation in causal inference. And on the other hand, causal data simulation is also helpful for determining the sample size for in a RCT, in a randomized control trial, so that you could do trials in a more efficient way. Okay, so this brings us to the goal of this talk. So we aim to develop methods for estimating the full distribution of the potential outcome and simulating data from estimated or specified causal models. And so there are two features involved here that we would like to highlight. The first is a distributional component. So here we are looking at the distributional estimate, distributional treatment effect. So the method needs to be able to estimate a distribution. And the second component is about data simulating or sampling or generation. So we need to also require the method to allow us to draw samples from your causal model. So that's the generative component. And now let's look at how to do that. So to talk about that, let's maybe move one step back and forget about causal inference for now and just look at the general distribution estimation problem in classical statistics. So if we're just given two random variables, x and y, and both of them can be multivariate, and the target is the distribution, in this case, it's a conditional distribution of y given x. And so x can be the empty set, then it's just a marginal distribution of y. Okay? And this is exactly like without X, this is the density estimation problem that we are familiar with. And in the conditional setting, we can, to estimate a conditional distribution, we can apply methods like quantile regression, distributional quantile regression. So there have been a bunch of methods from classical statistics to do that. And so there might be some potential drawbacks. For example, some of these methods are parametric. They make parametric assumptions, which can be good because it could allow us to do likelihood-based inference, but sometimes it might be restrictive for many real-world applications. And some of the methods are non-parametric, but they tend to suffer from high computational cost, especially when a sample size grows large. And they are also not very scalable to high-dimensional cases. And for example, like quantile regression is even tricky to define quantiles in a high-dimensional space. But more importantly, sampling is non-trivial for these methods. For example, if you do kernel density estimation, you get your kernel density estimator. But then if you were to sample from this, if you are asked to draw samples from this estimated distribution, you still don't know how to do it. It's not non-trivial. But of course, we have excellent literature on sampling. So you could, in principle, apply methods like MSMC to your estimated density, and then you can draw a sample from it, but it's non-trivial, and computationally it could be quite involved. Okay, so it seems like we are not fully happy with those existing methods in classical statistics. And what we are going to do is we look around, we look at other fields and to see if people from some other fields have been looking at the same problems and what their potential solutions are. And so if we look at machine learning area, and these days the most popular field in machine learning is generative AI, and they are actually trying to achieve the same goal. So the goal of generative AI is to generate new samples from your observed data distribution. And so that's, in a sense, exactly to learn a distribution. And over the past decade or so, more than a decade, they have been proposing a lot of great modern deep generative models, such as diffusion models or generative adversarial networks. And you might or you might not have heard of this method, but I'm sure you must have heard of OpenAI or ChatGPT. And if you ask them to produce an image, then the underlying model is actually DALL-E, which is one of the state-of-the-art diffusion models. So you might have used it before. And these are examples of images generated by DALL-E. So you can hardly distinguish these pictures from what could have been generated by human artists. Right, so these methods look excellent. So they have been excellent for images, text, or video generation. But then what about other types of data? What about scientific data, clinical data, and other application scenarios of statistics? And so the thing here is, if we in our daily research, we have a statistical problem in hand where we need to estimate a distribution, do you feel comfortable to grab like a diffusion model and plug it into your current procedure to estimate a distribution? You might usually not. So it's not so easy to do, although it's fantastic for images. So then basically now for this problem of estimating a distribution, on the side of classical statistics, where people have been studying density estimation for decades, and in machine learning, people have been studying like deep generative models for more than a decade now. But both seem to be not very ideal for our purpose, where we want something. So we are wondering if there's something in the middle that is potentially as simple as classical statistical methods, but also as flexible and powerful as machine learning methods. And if we have such a tool, then we will be able to, we will feel comfortable to just plug this tool in our procedure or develop new methods based on that. Okay, so in the next few slides, we're going to try to make an attempt to propose such a solution. Right, so now we're going to present a distributional learning framework via generative modeling. So again, the target is the conditional distribution of y given x, or the marginal distribution of y if x is an empty set. So the idea here is to build a generative model to describe the distribution of y given x instead of using density function or CDF or quantile function. So that's to say we write the function y, we write the response variable y as a function g of predictor x and some additional noise variable epsilon. And so epsilon follows a predefined distribution like a standard Gaussian. And this map G is often parameterized by neural networks. And so under this modeling framework, the goal of trying to learn of estimating a distribution becomes to find a transformation of a function G such that the distribution of G of x comma epsilon for any fixed x, and the randomness comes from epsilon. So this whole random variable follows the target conditional distribution of y given x. So that's a goal of generative modeling. And so what can we do? So once we achieve this goal, what we can do? So once this goal is achieved, we essentially have a model G that allows us to sample from this target distribution by sampling epsilon and fit them into the model G. And with that, we can basically estimate everything of this distribution based on your sample. And so we're going to look at more concrete procedure in 1 or 2 slides. And so now we try to learn distributions. We need ways, we need metrics to assess distributions. And what we're using here is slightly different from what people have been using in deep generative models. So we use proper scoring rules. And in particular, we use one of the most commonly used proper scoring rules called the energy score, which was proposed by Tilman Gniting and Adrian Raftery, who were both at our department. So given a distribution, a candidate distribution P, and a single observation Z, which is a fixed value for now, the energy score is defined as the following. So the higher the score, the better it is. So if we first look at the second term, it measures the expected distance between any random draw from your candidate distribution and this fixed observation. So we hope this, like any random predictions from your candidate distribution would be fairly close to that observation. And in addition, we also have the first term, which measures the expected distance between 2 random draws from your candidate distribution. And so we hope this term to be not too small, so as to avoid the degenerated case of a point mass. And the good thing about this energy score is that it's a strictly proper scoring rule, in a sense that now if we take expectation of the energy score with respect to the observation, then the expected energy score is maximized if and only if the candidate distribution is the same as the true distribution of your observation. And so this kind of optimality property can be make use of to design a loss function based on the energy score, which is exactly what we're doing in our method ingression. So its name also comes from energy score. So we define the ingression solution at the population level as the minimizer of the expected negative energy score. And so here, each of these candidate distributions are the distribution induced by our generative model when we have a G. So that depends on G. And another good property of the energy score, which was also one of the important reasons why we choose this as our loss function, is that it's computationally very easy to estimate. So we can actually write down this objective function explicitly in this form. And if you look at this form, it's not so different compared to a standard regression objective function. So the first term, because this is L2 norm without the square, so in a univariate case, it's a median regression, so it's mean absolute error. And so we have the true observation of response and a random prediction from the model. And in addition, we also have the second term, which encourage the model to not ignore the noise component epsilon. So it's kind of encouraging the model to have sufficiently large variance. Okay, so because of the fact that the energy score is a strictly proper scoring rule, we can immediately have this proposition which says that when the model is correctly specified, which is hopefully a very mild assumption if you parameterize G by neural networks, this ingression solution G tilde of x comma epsilon follows this target conditional distribution of y given x for all x within the training support. And so this kind of serves as the basic justification for ingression to learn a distribution. Okay. So once we fit the ingression model, we have an estimate for the distribution. And what we can do about it is that we can estimate all the functionals of this distribution, like the main quantiles or whatever, and by Monte Carlo. And so here's a procedure. For any fixed test point x, we can first draw a sample of epsilon from your like specified noise distribution, like usually a standard normal. So you draw a sample of size m, and then you get your fitted ingression model and this test point, and you fit this test point and the sample of epsilon into your ingression model. And this one, so g tilde of x comma epsilon I with I from 1 to m, is actually a sample of the estimated distribution of y given x. And so if your model is doing well, if the estimated distribution is fairly close to the true distribution, then that's a good that sample would be a good approximation of a sample from the true distribution. And then we define the estimators of conditional mean or conditional quantiles as the empirical mean or empirical quantile of this sample. So that's what we mean by sampling-based inference or estimation. Okay. So we provide R and Python packages for our methods, which can be like used in a really standard way. So I just want to ask question, how many people in the audience actually use R more often than Python? Please raise your hand. Okay, quite a lot. So then let's look at the demonstration in R. So it works like in a really similar way as GLM. So you just load the ingression package, and there's a function called ingression, which is helping you do all the model fitting, all the neural network fitting, stochastic gradient descent. And you don't have to worry about it. Just apply this ingression function to your data matrix X and Y. And then you create an object called ingressor. And then you call this built-in function predict with a specified type for mean prediction, quantile prediction, or sampling from your estimated distribution. So that's how you can use it. Right. And then I'm just going to give you one simple numerical example to give you a rough impression about how this method works. So here it's a simulated setting. The training data comes from, so the true function here is a sigmoid function, and it's heteroscedastic. And the test data is the same sigmoid function, but it has a slightly larger support for x. So the training support is about -4 to 4, and the test support is about -10 to 10. And we first, like as a comparison, we first do fit neural network quantile regression for 3 different quantile levels represented by 3 different colors. And so each panel here corresponds to a certain neural network architecture, so a certain number of layers and number of neurons per layer. And so you can see the results look quite messy, and we have a lot of quantile crossing issue. And also the neural network model can generally not extend beyond the support. Like out of support scenario is really performance is really bad from here. And in comparison, we keep all the hyperparameter settings the same, and here's the result from ingression. So just visually, the first impression is it's quite clean compared to the neural network performance. And apart from the first 2 cases where you can see the hidden dimension is only 10, so the neural network is too small to capture the nonlinear function. But apart from those 2 cases, it generally performs really well, and we don't have quantile crossing issue because we define the estimators as the empirical quantiles. And it usually can extrapolate reasonably well beyond the training support. So, and it's also very robust to different hyperparameter choices. Even for this one, the architecture is already kind of crazy. It's 20 layers and 10 hidden dimension, 1,000 hidden dimension. So that's to say, we might have found such a solution which lies in between. So ingression looks like a simple, flexible, and robust tool for distribution estimation, and that's the case because compared to classical statistical methods, ingression can make use of the expressive capacity of neural networks to alleviate parametric assumptions, and is also scalable to high-dimensional X and Y, and we've been also applying this to very high-dimensional applications like climate data, where the dimension is it could be more than 1 million, and we don't have like problems like quantile crossing and so on. And compared to modern generative models, ingression is much simpler, so computationally it's much lighter, and it has fewer tuning parameters. And also, instead of focusing on just generating images or text, we focus on downstream estimation and inference. Yes, please.
Can I ask you a little bit about like bias variance trade-off kind of stuff? Because so in the optimization,
Yeah.
you're searching over some distribution class,
Yeah.
or I guess like parameterized by a neural network.
Yeah.
G, like that G and
Yeah.
allographic G.
Yeah.
So what's like the price you pay? Is it clear the price you pay for making that very expressive and like potentially
Yeah.
having too many parameters? And how do you think about that with the energy score as the objective?
So yeah, thanks for the question. So one thing about using neural networks is, so if we look at the same estimate, the same like conditional mean, if we're both fitting conditional mean, if we use neural networks or linear models, like it's one thing is about model specification, whether it's going to be correctly specified. If the true function is not linear, then you have to use something more expressive. But if, of course, if the true model is linear, then you pay a price by using a larger model class. So that's one thing. But also you can look at different objective functions. So here we are trying to estimate the full distribution, but in the end, if the goal is always like conditional mean, then it's not like statistical most efficient way to estimate the distribution first and then get the mean out of it. And so you also pay a price there in principle, in a sense that you try to estimate more, which is some kind of nuisance, which we don't like in statistics usually. But it's not what's happening in practice, I would say. So in practice, even for the same target, ingression still performs empirically better than regression given the same model class. And that might be some like optimization neural networks issue, like whether it's helping with overfitting or yes, but that's something we need to investigate further. Yeah, I hope this answers the question.
Maybe follow-up question, like, are you able to, so if you had a downstream task in mind, are you able to kind of incorporate that in the optimization problem of ingression in a way where you can
more targeted somewhere?
Yeah,
exactly. That's a good point. So you can, because this is simply a minimization problem.
Yeah.
If you have another objective, you could quantify it and like
add as a penalty to it.
yeah, exactly. That's sometimes what we do. We are going to do it later, actually, with yeah. Yes, please.
Can you explain again what the capital G is here?
You mean the this one?
Yeah.
So that's the function class for G. So in practice, we use a neural network class.
Okay, so you get like, I guess, what is a neural network class? The outputs of a neural network?
The outputs of neural network?
Yeah, what is neural network class?
So it can be something like you fix a hidden dimension and the number of layers, but you could also vary that. You consider a few combinations, and each like possibility of the coefficients of the parameters of the neural net would correspond to one model in your class. Yeah. Yes.
So why don't you continue? So I'm happy to wait until the end if you prefer. But I guess this is another version of Armin's question. That is, I wonder if you can think about the second term in that utility function as some sort of implicit regularizer that in some sense is addressing the,
Yeah.
the penalty of the dimension.
That's a good point. So that's also at some point we had in mind, and we still think that's the case, but we hadn't fully understood why like what kind of implicit bias is imposing to the, especially the gradient descent training. So that's something very interesting, but not clear yet now.
Well, and this is another subtlety, now that you mentioned,
Yeah.
stochastic gradient. So I imagine you guys are using stochastic gradient to.
We sometimes use full batch gradient descent.
Okay. Well,
Yeah.
because, I mean, the reason why I'm bringing this up is that, you know, this fixed budget stopping rules for stochastic gradient also introduce regularization
Yeah.
problem.
But early stopping.
So the question is that, I mean, you may have 2 or 3 ways in which you are addressing the problem that kind of hit it in the calculation.
Yeah, that's true. I would say compared to like standard neural network regression, the other components are kind of the same because we also use gradient descent for standard neural network training and we early stop. And the only thing different is this part. So yeah, thanks. All right. And so we almost forget about causal inference, but let's come back and look at causal inference. So our objectives are, we have 2 objectives. One is to estimate the full potential outcome, full distribution of the potential outcome. So it's a distributional estimate. And the other thing is to simulate data from estimated or specified causal models. And in the following, we're gonna talk about 2 papers, hopefully, maybe somehow briefly about the second one. So we consider 2 settings for the 2. So the first one is a case where, in addition to observing the treatment and the outcome, we also observe an instrumental variable. And then we allow for the existence of unobserved confounders. And then the model needs to somehow be able to capture the latent confounding. So that's going to be the tricky part. And in the second setting, so we don't observe an instrumental variable, but we have a bunch of observed covariates, which can be the confounders or the mediators. And so, and we have a slightly different goal there. We want to parameterize the model around the marginal causal effect, so around the marginal causal model. And then we want to be able to simulate data from the specified causal margin. So we're going to go into details about both. So let's first look at the first paper, distributional instrumental variable method. So this is a joint work with Anastasia, James, and Nikolai, who, so all of them are at ETH Zurich. So here we have a treatment X, outcome Y. And the question we're interested in is what would happen if everyone were given treatments X equal to a certain treatment level, little x. And that's to say our estimate is the dual interventional distribution, if we use Pearl's language, of Y given to X. And or if you use potential outcome language, then it's the full distribution of your potential outcome Y of little x. So we allow for hidden confounders. So there might be some unobserved variables that are causing both X and Y. And so that makes the whole thing trickier because we can't just do standard regression or regression of Y on X. And that's going to be biased. And so so now we observe an additional variable, which is called an instrumental variable Z. And so here Z is directly affecting X and it's not directly affecting Y and it's uncorrelated from H. So these are the assumptions for the IV. But we consider the non-parametric IV model where both the treatment model and the outcome model can be a non-parametric, nonlinear. And the tricky thing is because of the existence of hidden confounder, these 2 noise terms, eta X and eta Y, are correlated. Right. So because this is a like causal estimate, so we just observe a data, so we have to first study the identifiability of the estimate. And here's the result. So under some like typical assumptions in non-parametric IV, we can show the interventional distribution, our estimate, is uniquely determined from the observed data distribution of XY given Z. And so then this identifiability result directly suggests a method to first estimate the observed distribution, and that's going to be sufficient to identify these estimate the interventional distribution. Okay, so this is directly this is exactly what we're going to do. In the following, we're going to propose methods to estimate this observed distribution based on ingression So we first introduced generative models for this observed variables x, y, z. And so what we're doing here is we have two generative models for both the treatment given the instrument and the outcome given the treatment, because given conditional treatment, they are independent. And the tricky thing is, as we said earlier, these two noise terms are supposed to be correlated because of the existence of hidden confounder. And to model that, we parameterize these two noise variables as a function of an independent noise and a shared noise variable. And so this shared noise variable is supposed to capture the correlation between these two confounded noise. Okay, and all the epsilons are standard Gaussian. And once we build such generative model, sampling is trivial because we just draw samples of epsilon from standard Gaussian, and then we go through this models hx, hy to get the etas, and then we can fit them into the model G to get a sample of x. Then we put this x here and go through this model F to get a sample of y. Okay, so that's how we can sample from our model. And then here's how we define our methods: distributional instrumental variable estimation. So it is nothing but applying ingression to this distribution of x, y given z. So in this case, our kind of response is a joint pair of x and y, of treatment and outcome. And previously, the predictor is now the instrument. And so I hope this loss looks familiar to you. So we have the ingression loss, the energy score, and in the first term, we have the observed response, the observed pair of x and y. And then in the second term, we have a random sample from your generative model, which we can do according to the last slide. And then in the second term, we penalize the difference. We try to encourage a larger difference between two random draws from your generative model. Okay, so that's the objective function. We minimize it by gradient descent, and we denote the DIV solution as a minimizer of this objective function. So we use this F star, we use star to denote the DIV solution, and this is what we can prove for the DIV solution. So we note that this F star is the outcome model, and HY star is the noise associated with the outcome. And so we take the DIV solution here, and we fix the value of x, and epsilon are drawn from standard Gaussian. And what we can prove is this whole random variable follows the target interventional distribution of y given do x. And so this is exactly what we want to estimate. And now what we can do is we have a model that allows us to sample from this model, from this distribution. So that's kind of, we're very good with the goal. But we can do something further. Of course, we can also estimate the functionals of the interventional distribution. For example, if you are interested in ATE and you take two treatment levels, x1, x0, and what you do, you can actually get the estimate the full interventional mean function by taking the mean with respect to the epsilon. And empirically, you just draw a large sample of epsilon, and then you compute the empirical mean. And you can do the same for the interventional quantiles. So instead of taking the mean over epsilon, you take the quantiles now with respect to the epsilon. And then you can get the estimation for the interventional quantiles. Okay, so that's how we get an estimate for the full distribution of your potential outcome. And then you can, from there, you can compute all the estimates for the ATE or QTE, depending on who interested. Okay, so and now I'd like to add one more point. So we've mentioned before, according to this identifiability result, that estimating the full distribution is going to be sufficient to identify this estimate because of the identifiability. But we also want to highlight that sometimes estimating the full distribution is also necessary to identify the causal estimate. And I'm going to illustrate that through this simple example called an under-identified IV case. So in this case, we have one binary instrument taking like values 0, 1. You can think of it as a case where you have data from two hospitals, and the instrument is simply the hospital index. And you have two continuous treatments like dosage of 2 drugs, and then you have one single outcome. And for simplicity here, we assume the outcome model is a linear model. And then the causal estimates are the 2 coefficients, beta 1, beta 0, beta 2. And in this case, the standard IV regression, 2-stage least squares, would fail. And I'm going to tell you why. So in 2-stage least squares, what we're doing is, in the first step, we regress the 2 treatments on the IV. And so then the 2 fitted variables, these 2 conditional means, is what we get out of the first stage. But the thing is, here we only have 1 binary IV. So these 2 fitted variables are going to be collinear because of the binary structure. And then in the second stage, what we're doing is we regress Y on these 2 fitted variables. And then we're going to be in trouble because these 2 variables are collinear. So we can't, we do regression, we can't identify the regression coefficients. And so that's why the standard 2-stage least squares would fail. But that's unfortunate because this problem is identifiable, actually. So the distributional identifiability still holds, in the sense that under this assumption, which we're going to explain in a second, we can show these 2 coefficients are uniquely determined from this observed distribution of x, y given z. And so it directly means if your procedure is not lazy, it's really like working hard trying to estimate the full distribution, then you are going to be good because you have identifiability from the full distribution. You can identify those 2 betas. But if you kind of do something, do a shortcut, you just do the mean regression by 2-stage least squares, then you are going to fail in this case. And the assumption is quite intuitive. So it means that the conditional distribution of the treatments given the IV taking 2 different values are going to be different in more than just a mean shift. That's what this assumption is trying to say. So it means these 2 distributions are different in maybe the variance or their quantiles, but as long as there's more diverse information in the difference between the 2 distributions, a distributional procedure is going to be able to make use of that information to identify the causal estimate. But if you simply look at the mean, if like a mean-based procedure wouldn't be able to make use of that information, even if there existed one. Okay? Right. And yeah.
Just a quick question about that. So, if you consider not 2-stage least squares, but like methods that people have developed that are a little bit more, kind of maybe use more information than just the mean, would
Yeah.
you see the same?
They will do something slightly better.
Yeah.
So, but they wouldn't have the same. So basically, under this exact setting, there's no existing method that can identify beta 1, beta 2. Although this problem itself is identifiable. Yeah. But you can make some assumption, like if you have difference also in the variance, and a procedure that is trying to exploit the variance would be able to identify. So you can make something like that. But here we just say, as long as there's more information than the mean, then a distributional procedure is good. Yeah. So that's a message. So we also provide R and Python packages for FDIV, and it also works similarly to ingression. So you have this function div, and you apply it to your data matrices, the instrument, treatment, and outcome, and then you train it. So all the gradient descent is implemented in this function, and then you call predict with a specific type for estimating the interventional mean or interventional quantiles, or sampling from the estimated potential counterfactuals. And here's like an illustrative example of what we can do with DIV. So basically, each panel, so each row corresponds to a different treatment level, so different values of X. And then what we fit a DIV model, and we can draw samples, and we plot the histogram of them. And you can see, like, depending on different treatment values, the distribution of the potential outcome, they really vary a lot. So previously, if we only look at something like ATE between, for example, these two treatment levels, then you're going to lose a lot of information. So you just compute the mean here and the mean here, and you take the difference. But you couldn't see how large the variance is. So in some cases, maybe people are still interested in the remaining information. So that's why a distributional estimate could be more useful. Okay, so we can also easily extend it to handle covariates, additional covariates, and to estimate conditional interventional distribution. And so it's very natural to extend it. So we just add the covariates W to your generative model, to both of these two generative models. And then we learn the DIV model to fit the joint distribution of XY given both Z and the additional covariates W. So just very quickly to show you a numerical example, here is about quantile treatment effect estimation for lots of quantile levels. And we compare against IV quantile regression and previous methods that can do this quantile treatment effect estimation. And you can see like the green one is from DIV. And for all different quantile levels, the results from DIV is quite robust if we look at the RMC of the quantile treatment effect estimator. But the other methods are doing okay, like when we look at the median, around the median, but if we go to the tail part, it's not performing well. They're not performing well. And another simulation setting is a kind of under-identified case where we simulate the data such that the conditional distribution of X given Z depending on the mean in this linear way, but the variance also depends on the instrument. And so alpha controls how the dependency of the conditional mean on the treatment. And so when alpha goes to 0, the mean no longer depends on the instrument. So whatever method that is trying to exploit the mean would fail. That's something we're expecting, but that's also something that's happening here. So we compare DIV with the existing IV approaches. And for larger alpha, when there's sufficient information in the mean, all the methods perform like more or less okay. But when alpha tends to 0, DIV is the only method that wouldn't fail, that can maintain the performance, while all the other methods would fail. Okay. And we also apply the method to an economic data from this famous paper from these three Nobel Prize winners. And so we studied the treatment effect of the institutional quality on this log GDP per capita. And so here they are trying to argue from the economic background how two-stage least squares is giving a reasonable performance. So we also take two-stage least squares as a reasonable approximation of the truth. And so now we compare. So first of all, the purple one, OLS, is off. So it's not the same as two-stage least squares because there's hidden confounder. And our method, DIV, the green one, we can see it matches the two-stage least squares quite well, at least for the majority of the region. And so it's a good sign because this is an extremely challenging scenario for neural network-based methods because the sample size is below 100. And it's also a linear case, but we use actually a more complex model class. But you can see it still performs reasonably well, and that is the kind of a good approximator of the ground truth. Okay, so the takeaways about DIV is that it's a distributional approach for causal inference in the IV setting that can easily handle multivariate treatments, outcome, and covariates. And we can show it sometimes have more identification than mean-based approaches like two-stage least squares. And it's trying to estimate a full distribution of the potential outcome. And it also enables sampling of single counterfactuals. So I probably need to go very fast about this second work. So it's frugal, flexible, faithful causal data simulation via regression. And it's a joint work with Lin Yang and Robin Evans from University of Oxford. So here the target is the same. The central interest is still the interventional distribution, but because we have some additional covariates which could also affect Y, so we emphasize this on marginal interventional distribution where we don't put Z here in the conditioning set. And so we have slightly different objectives. And so apart from estimation of simulation, which would be probably mostly the same as before, but we also want to do something for the parametrization. We want to describe the joint distribution of XYZ, in this case, around the causal margin, because that's the central interest. And so that's to say, for parametrization, we have a few desiderata for a good parametrization. So first, it needs to specify the full joint distribution of XYZ. And the second is it needs to have a component that is a marginal structural model for this causal margin. And also, we hope each component to be chosen variation in a way that is variation independent, meaning that you can change your causal margin without changing the other parts of the distribution, like the confounding effects or the covariate distribution. And we also hope the method could be non-parametric flexible, so it's hopefully applicable to lots of real scenarios. And here's a proposal from Robin and his co-author before, called frugal parametrization. So idea is we try to decompose this joint distribution of XYZ. And the simplest, the easiest part is the distribution of the covariates and outcome. We just take it out first. So that's the past distribution, what you observe before the outcome. And then we said we promised that we are gonna have a specific, a separate model for the causal margin. So here, that's a causal margin that we promised before. And then we put all the remaining term in the association part. So in this part, so that's a parametrization. But unfortunately, it doesn't satisfy the last desideratum, because it's parametric. Unfortunately, the causal margin needs to be parametric. So, and to address that, we propose generative non-parametric extension of frugal parametrization. And so the method is going to be based on ingression. So frugal and ingression, we come up with a name for ingression. And so what we're doing is, like, we basically follow the idea of frugal parametrization, but we use generative models. So for the past model, we built a generative model. So there's G of some noise variable to match the distribution of X and D. And for the causal margin, we have a conditional generative model that depends on X and some noise variable to match this causal margin. So that's our marginal structural model. And then we put everything else in this association remainder. And we can prove it still has all the nice property of frugal parametrization, especially that we can change the causal margin without affecting the other parts. And one counterexample of variation independence is if you have two components like X given Y, the distribution of X given Y and Y given X, then you can't simply change the one without affecting the other one. So that's a violation. Okay, so basically that's what we can do. And the method, how we do model fitting, is based on ingression. So forget about the details. You can see these two objective functions are ingression. So it's an extension of ingression, although it's more involved somehow. So then after fitting a regression model, we can draw samples from a lot of distributions. Like you can draw sample from your causal margin given a specific treatment level, and you can also draw samples from a joint distribution of XYZ, and also you can specify a new causal margin. So you can replace this F star by whatever causal margin may be a null hypothesis in your hypothesis testing, and plug it in here, and you are able to keep all the confounding effect and covariate distribution the same as the observed data. Okay, so we've applied this regression to a real large-scale trial data called LEADER trial from this company Novo. And unfortunately, due to the interest of time, I might have to skip this, but it's even so that's roughly the covariate structure. We have some static covariates and some time-varying covariates. And it's a longitudinal structure. We have multiple time steps, and the outcome is a discrete one. It's an event indicator. So we apply regression to it, and we're able to validate that regression can faithfully capture both the covariate structure and the event frequencies. And so just to quickly summarize, we talk about distributional causal inference. We have two objectives that we keep emphasizing throughout the talk. So first is we aim for estimation of the full interventional distributions, or let's say the full distribution of your potential outcome. And we also want to simulate data from estimated or specified causal models. And for those two objectives, we've developed a few several methods. Like the foundation is in a non-causal inference setting. So it's ingression, which is a simple but flexible generative method for distribution estimation. So it has the two components, distributional and generative. And then so DIV, the first method is ingression plus IV plus instrumental variable. And the second method for ingression is the combination of ingression with frugal parameterization. And there are some favorable features of these methods that I would like to highlight in the end. So first of all of the approaches are non-parametric. So the model class is very flexible and expressive thanks to neural networks. And computationally, these methods are very scalable to multivariate cases, high-dimensional outcome treatments or covariates. It doesn't suffer from any computationally. And also, we provide softwares for all of three methods, and in both R and Python. And we've also shown that how robust those approaches are to different hyperparameter choices. So it doesn't really require very much hyperparameter tuning. So that's why it could be potentially very user-friendly. Okay, so that's all. Thanks for listening.
The 2 minutes for some questions.
I guess first question is clarification regarding this optimization. Are you dampening the noise variables for each sample and then using those?
Yeah, that's a good question. I didn't clarify. I didn't have time to. So in practice, we have the empirical loss, right? Which replaces E by like the sample mean. And for each observation, how we do with epsilon is, so we actually have, you can imagine we have a big population for epsilon, but at each gradient descent step, at each iteration, we draw new samples of epsilon for each observation of xi and yi. And we only use 2 samples of epsilon at each iteration for each observation. So that means if the sample size is n, and if you do full batch gradient descent, at each step, you sample 2 n epsilons. And then at the second step, you sample like another 2 n epsilons. And so in the end, if you have t iterations, you get to observe a large sample of epsilon. Yeah, it's not important. So basically from uniform to Gaussian, you just apply Gaussian CDF. So that's what in your network needs to learn. But if you kind of make it really hard, you do a super skewed distribution, then that's going to be a problem. But you don't have to have that problem.
Is realizability assumption on the neural network class, or is it like potential predisposition?
Sorry, I couldn't hear the.
Like you need like some kind of realizability assumption on the neural network class.
Oh, yeah, that's a good point. So empirically, we don't apply any like regularization. Well, we do early stopping, right? Because we have to stop at some point. So, but we don't do things like spectral normalization or even batch normalization. You could have that. We have that option in the package, but we don't usually keep it on. So it's very light. You don't have to do like sophisticated regularization for your neural network training. But in theory, you have to make some like smoothness assumption for the function class in order to prove something. Yeah.
This one more qualification question. So like when you great origin class, the first term will have epsilon I.
Yeah.
It's like connected with the realization. That's connected with the response. So with the observation.
Yeah.
So is that the same one you use?
Yeah, that's the same one we use.
And then you have one.
The same 2. We have 2 samples, right? So for the first term, we use both of them and divide by 2. Yeah, we use the same one.